This is the set of notes that goes along with the gassing up note sheet. So make sure that you're looking at the right sheet here. It starts off, it's pretty short and sweet. It just goes through some of the properties of gases and some of the basic ideas that we'll be talking about this unit. So to start off with here, properties of gases. The first thing to keep in mind is that gases are always moving. So even though when you're holding, say, your hand in the air, even though you don't feel the particles moving, they're always moving very quickly, actually. And it's because they have temperature. Remember that temperature of something is its average kinetic energy, so the higher temperature something has, the more its particles are moving around. And so unless something is at absolute zero temperature, it's going to have some sort of particle motion. The next thing here is talking about its shape. So it takes on different shapes and actually different sizes here, depending on what container it's in. So gases are very, very susceptible to being changed in terms of how they're shaped and what size they are. And we'll talk about some gas laws later, but it says expand or compress. So if you put pressure down on a gas, it's going to condense into a smaller area. If you lower the pressure on a gas, it's going to expand. Okay, so number 4 here, it has mass. So what I mean by that is that it's made of atoms. Okay, those atoms have, protons in them. They have neutrons in them. So there's mass in there. There's they have weight actually to them too. But all the particles are flying around in the air, so we don't really feel them that much. But there is mass. This is super important in terms of how gases work. So the pressure that gets created is caused by collisions. Collisions between the particles as they're bouncing around and the side of the container. And I'll talk about that a little bit more in the next set of notes. But basically how it works is if a particle crashes into the side of its container, it's exerted a little bit of pressure there. Now if you take an entire container full of gases, that's going to have millions and billions of particles in there, just an unfathomably large number of particles. And as those particles hit the sides of the container, every time they do, they're pushing the container out a little bit. And so that's what creates the pressure. There are a couple things that can affect that, and as I said, I'll talk about that in the next set of notes. In addition, with the pressure, things move from high to low pressure. So you might imagine if you, say, had this tire here in this picture and you pressed on the valve, you would feel air coming out. That's because there's high pressure inside the tire. The air comes out so that it moves from the high pressure situation to the low pressure situation. Basically, the reason for that is because we have all these little particles colliding with one another, and if they're more crowded together, they're going to want to try and spread out from one another. And so there's more space in the low pressure area for the particles to move around, so they move there outside of the high pressure area. Here's another thing. Heated gases are going to spread out more, which means that they rise. Cooled gases sink. And if you've seen a hot air balloon, you've seen this phenomenon at work. So what happens is they just heat up the air particles. The air particles become so light that it can lift the balloon and a person in a basket. And so it's a pretty significant difference there. The next thing here is that they diffuse. And you have to know, diffusion means like moving through a substance. So gases move through different substances. They can move through other gases, or they can move through a solid. For instance, I do this demonstration where I put some vanilla inside of a balloon at home, and I blow up the balloon and I tie it off, and there's no vanilla on the outside or anything, and I bring it into the room, and I just leave it sit there, and then everybody comes in and they say, "Why does it smell like vanilla in here?" And it's because the vanilla smell has moved through the balloon. It's actually gone through the sides of the balloon, and it's not that the balloon has holes in it per se. What it is it's that the little gas particles can move through the matrix of the different solid particles, and it can move all the way through the balloon and come out to the point where you can smell it. So they diffuse. Here it says through gases, but they diffuse through all sorts of things. A gas can diffuse through a liquid, it can diffuse through a solid, it can diffuse through other gases. So all right, for temperature, this is pretty important. In this unit, we're going to focus on Kelvin temperature. The reason is because it's an absolute scale, so it doesn't have any negative values there. 0 Kelvin is the coldest you can get, and it's because we talk a lot about proportionality here. And if we're talking about proportional temperatures, we need to have them in an absolute scale. Celsius having a negative temperature doesn't actually make very much sense if you're talking about comparing them, because it's not like a negative temperature in Celsius means the particles are, have negative energy or they're moving backwards or something along those lines. So yeah, we put it in Kelvin so that we have the proportionality there. Remember 0 Kelvin, that's when all particle motion stops. It's called absolute zero. So converting between Kelvin and Celsius, you just use this equation. You just add 273 to the Celsius temperature. So if you want to go ahead and try and do that with these two, try and figure out what they would be in Kelvin, you can pause the video and try and figure it out, and then I'll show you the answers here in just a second. All right, there they are, 385 and 241. So again, we're just adding 273. Negative 32 plus 273 ends up being 241 because that negative 32 is kind of like a minus. For pressure, we've got a bunch of different units. Atmospheres are the normal units. 1 atmosphere is normal atmospheric pressure. Additionally, we have 760 millimeters of mercury. Where this comes from, if you see this column over here on the side, this is actually a column of mercury. If you take a tube of mercury and you turn it upside down inside mercury, well, actually, I'll go back. I'll talk about this experience that I had when I was a kid, first of all. So I had this experience when I was a kid playing in the bathtub. My parents would give me cups to play with in the bathtub. I didn't have like rubber duckies or anything, but I had these cups, and what I'd do is I'd put them under the water, and then I'd turn them upside down, and I'd pull them up, and I'd see that the water stayed inside of the cup. And I thought that was pretty cool. And it turns out that that happens only to a point. And actually, for water, it's a pretty high point. So it's something like 30-something feet, like 32 feet. So if you take water and you, like if you can imagine like a 32-foot tall glass, and you put it underneath the water at, say, Lake McBride, and then you turn it up on its end, you would get a column of water that was sitting there, just like this, and it would go up 32 feet. Now, if you get anything above 32 feet, the atmospheric pressure that's pushing down on the outside of this liquid is no longer enough to hold that column up, and so you get a vacuum up in the top. All right, and so they do this, but they do it with mercury instead of water, because mercury is much more dense than water, and so it can only sustain here 760 millimeters of mercury under atmospheric pressure. And then the higher the pressure, the more mercury it can hold up. And so what we're showing you over here is actually something that's called a barometer. It measures atmospheric pressure. 760 torr, that's the same thing as a millimeter of mercury. Someone tried to name it torr after this guy Torricelli, and the name didn't really take off, so we still kind of use both. Kilopascal is the metric unit for pressure, so a pascal is actually a Newton per meter squared, and a kilopascal is 1,000 of those. So that's how that works. So we'll mostly work in atmospheres, this unit, which means that anything that's not in atmospheres, you kind of have to convert. So, for instance, go through, try and do these conversions on your own. I got rid of that last one there, so don't worry about that. I'll tell you here, this one it says 220 atmospheres, so that's a really high pressure. And so if we look at millimeters of mercury up at the top, there's 760 millimeters of mercury in 1 atmosphere. So if we have 220 atmospheres, that's going to require quite a lot of millimeters of mercury, okay, in the order of 100 and something thousand, like 160,000 millimeters of mercury. So you can go through and do that calculation. It's just 220 times 760 and get that. This other one, we've got 1.5 torr. You can see here 760 torr is just normal atmospheric pressure. So 1.5 torr is going to be a really, really small number in terms of the pressure. So we take 1.5 and we divide it by 760, and that gives us atmospheres. So yeah, you should make sure to know how to do those conversions. We'll be using them in this unit quite a lot, so get comfortable with that. All right, the last thing here is just a little review on standard temperature and pressure. So you have to remember STP means standard temperature and pressure, and I want you to know that the normal standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere. So that's something you're going to just be required to know. And then this says, or any from the list, because I gave you all those values equivalent to 1 atmosphere. So if we have 760 millimeters of mercury, that's also standard pressure.